surface scanning as well as the depth. You can scan what is the layer or the material depositions. So all the things having either the light-based energy or wave-based signals to identify the inbuilt material qualities. So here I just list out the challenges in that is some of the challenges we have in the additive manufacturing system. So what are the things we are manufactured in additive manufacturing? Or either the SLS or SLM or fusion deposition machine, whatever it may be. So you have a complicated structure. So the part is complicated in the sense the testing or inspecting is also in a very complicated one. Even if you are using a coordinate measuring machine, the dimensions may be you can easily measure. So an intricate or a complex part is very difficult. It will be taking too much effort you have to put to get all the dimensions. So the next one is even here the material deposition and other material flow is in the level of micro or nano level. So you have defects or in a flaws. Have to find out in the range of nano or micro level. Even in the SEM and TEM, you are getting a flaws or an inbuilt material quality or morphology of the material produced is studied in the level of micro and nano level. So you have to adapt that one. So here the deposition itself, you have a nano deposition. So you may have a deeply embedded flaws and internal features may be varying. So the layer or a hatching distance or hatch spacing, everything will be varied. The atom level to atom level, you have to measure the distance between the two atom level. Either it's overlapping or intersecting, or you have a small gap. So that is deeply embedded in the particular things. Then what are the things you are manufacturing is a rough one, and the build one is having some surface finish. So depending upon the surface place, you are applying the parts to the application. So the surface place record is varying with application. So here you have to consider that part also. Then the grain structure. You have so many variables in the grain structure. Even the grain structure may be in a spheroid or tentrix or granular. So you have different types of grain size. Even the growth be leading to different shapes to the structure. So here the microstructure may be in a stable. In that cases, I have to more effort to analyze the particular. Then the reference. So you have an AICTE or a NIST, the National Institute of Standards and Technologies. They have some standards for all the bulk material testing or even other types of material testing. But in the nano level or in the additive manufactured parts, so even till the process is going on, what standards you have to follow. So here I just listed some of the standards to consider while doing experiments. Even one of my scholar has done the additive manufacturing process and used that AICTE 695 standard for testing in compression. So you have the compression as usually in a UTM. So micro UTM is there. In the micro UTM, you are doing the compression test, but the standard is I have to follow. So till the standards are developing. So most of the testing, the standards are not adapted or not assured by even the ASTM or NIST people. So here we have standards problems. Then the processing history is somewhat different. Then the lack of effective defect studies. So even the manufacturing, additive manufacturing, we are getting up parts and used for that one. The inspection or testing of the particle is most of the people are not doing. So study is end of the effect of defect studies are very less. If you are searching the literature survey, you can get some few literatures about this one. That's why even that ATAL is enforcing additive manufacturing is an upcoming thing. In future or 10 to 15 years, after 10 to 15 years, there may be a lathe, there may be a milling machine, there may be a machine. So you can do all the things with the printing technology. So even the metal printing also available. In cases, the old machineries or the conventional techniques will be observed. It's going to that. But what are the things we are producing in the new technologies, new things, we are not at all analyzing the effects of defects. So the defects is what? In the bulk material, you have defects in a different matter. If you are going for an nano level or an additive manufacturing, so you have defects in different form. So you have to thoroughly analyze that one. Then the method to see natural flaws are still being developed. So here the natural flaws, that is, if you are having one part with an aluminum or a titanium or vanadium, some materials. So depending upon the materials, the flaws will be differ. Even the same thing happened in the bulk material analysis or conventional manufacturing also have a same thing. The high part anisotropy. So in the 3D manufacturing or printing, rapid type prototyping, additive manufacturing. So you have each part having an anisotropic. So even in a same directions, you have a mild steel tensile test. You have a mild steel that the diameter is fixed, the length is 200 mm, and the neck for the holding size you have to turn. Then doing the experiments. If you are getting an ultimate strength or the yield strength for a material, it may be constant throughout that. But in case of additive manufacturing part, this is differ. So why this is differed in the sense, if you are pouring the metal, so in the melt pool, the lesser directions, you have one melting, then the other side you have another melting. So you have a small difference in the directional wise, you have a change. Similarly, the same direction sometimes it may be vary. So you have to go and thoroughly analyze. Then the critical flaws types, the size and distributions are not established. Even if you are magnifying 500 or a 600 or a nano level, Armstrong level, so that size is exactly determining the size is very manufacturing. There is an and direct energy deposition methods, metal additive manufacturing, they may be same. So even local peoples are using a fusion deposition machine, the PLA material, the ABS material, and other normal things. But the combination of as per the periodical table, you have so many metals. This metal combination is not done in the additive manufacturing. So in that cases, the defect terminologies, suppose the same defects may not be occurred in a vanadium or a tungsten or in a aluminum. So in that cases, they have a different terminology introductions. So that also going to be approved by some of the bodies, or it may be accepted by some of the standard journals. Then it will be coming. So this is still occurring in the part. Then the process specific defects can be produced. So even the process type, you have to follow some of the ASTM standard. So if you are varying this one, in that cases also you have an defects. Even in the slides, I'm just putting the density. The density, you have a hard isostatic pressing. So in that one, you have a small holes. Even in the hard state, you are compressing, but you have a small holes. So this is maybe controlled in the process parameters. So if the process parameters going beyond that one, that is the specific energy, formula, you have a standard formula. In that standard formula, for each machining, so you have to follow the range. That table also I have presented here. So in that cases, if anything is varied, you can have a defects. So that things you have to consider. Then the probability of detection data. You have a very little data. Even if you are going for a machine learning or something, the data, one of the data available for AM is very less. So here you have to increase them. Then the lack of return procedure for additive manufacturing products. So even in the ASTM, if you are searching, you have a few standards available for a particular few materials. Are also tabled here. We can discuss that one in the next. Then here, what happens if you are producing an additive manufacturing parts? So you have an inhomogeneity. The outer side, definitely you are pouring, melting, giving in a material in terms of micro level, nano level, small particles. Then visually, if you are inspecting, that may be continuous. That may be continuous, but you can't easily find. But if you're going for a normal casting, if you're boring a cast melted material in the mold, after that you can see some of the flaws in the open eye or the oxide layer, porosities, everything. Maybe you can have a visibility, but here you can't easily find out that one. So the first one, you have an inhomogeneity in the inhomogeneity identified in the literature for the additive manufacturing parts. So here, what is the inhomogeneity in the sense? Presence of impurities. So impurities present, the variation in grain size. So these things, even the distinct crystallographic texture, these things are not easily visible, and the visual inspection is not easy with a fair eye. So I have to go for visual techniques of the using light-based mechanisms. So here all of these items are controlled by the process parameter. This is occurred in the sense the process parameter will be is the problem. So here, what is the energy, the built energy supplied, then the path, and you have a material type. So material type. So here even the crystallography structures, if you are heating, that is melting and pouring the centering or depositing the materials. So the directionality of the grains in opposition to the direction of the heat flux. So this is the nature of depositing, that is the grain directionality. So other directions you may have a same thing. The other directions, what happen? It may vary. So that's why the previous slides explained that one is an anisotropic. Anisotropic in the sense that anisotropic is also a complicated. In that one also you have a complex one. So here the crystal structure exhibits small columnar grains. Some material also exhibits some fine dendritic structure. So you have a different structure. So I have to put more effort to find out the structure type, how the crystal growth is there, then how the directionality will be there, then where you have a voids, etc. So here the standards for heat, that is heating on the material depositions. Here there are 4 standards are described for the powder bed fusion technology. So the powder bed fusion technology, you have an SLS, SLM, etc. You have all methods. Most of the methods coming under this one. Here, nickel alloy, you have an ASTM F3050 standards. Similarly, if you are going for a titanium 6 aluminum 4 vanadium, you have to go for an AICTE F2924 technology. So each things will describing the procedure, what is the built energy, how to supply the part, then the feed rate, then the timing, etc. Flow rate, everything will be given. Then another thing, the titanium 6 aluminum 4 vanadium, then extra low interstitial thing. You have to use an ASTM F3001, then a nickel alloy with this standard. You have to go for an 3G. N is not applicable, S is surface sensitive, then I is an internal or a through thickness. Internal side you can get the details, then Y is applicable. Okay, Y is applicable. Suppose if you are selecting a visual thing, the microstructure you can't see, bare eye you can't see that microstructure, that crack and porosity, voids, etc. At the surface you can see, otherwise it's not possible. Then you have a mechanical property. The visual thing you can't get a mechanical property, that's not applicable. Then the geometric accuracy and the surface level you can see. Similarly, the ultrasonic method and an eddy current method, radiography, magnetic methods, liquid penetrant methods, stereography, acoustic thermography. So these methods are used to find the flaws or inspect the AM parts. So here each thing having some peculiarity. This is not applicable. That is, magnetic method is not applicable for mechanical properties as well as a geometric property, then the surface roughness. So the remaining thing, microstructure, then the cracks, porosity, void, you can find it from this magnetic method. Similarly, residual stress you can find. So you have a correlation with the methods and the properties. Then I have to go for how this happening in the field, that is FEM, you have to consider. So here that is the sintered. Already this layer is over, but in between you have an unsintered material. So you have an unsintered material. So all the field techniques, the laser sintering, direct metal laser sintering, then the selective laser sintering, then electron beam melting, selective laser melting comes under this fusion belt, the powder bed technologies. So here the laser scanning direction is in this directions. Here what happened, how the directionality is there. Along this directionality you have a grain growth, the directionality of grains in opposition to the heat flux. So that will determine the crystal structure as well as the grain growth. So here you have some of the granules, the particles, powder particles are not sintered, melted, are not having an attachment. Similarly, so it will having some porous and the unmelted part. So this is a simple diagrams where the cracks are the defects are generated. So these things already may be gone through in the manufacturing side, the material equipments side. So here in that basis, powder bed fusion technologies, whatever the things powder bed fusion technology, these type of manufacturing systems, the basic is this. So depending upon the particular equipment, this thing may be vary. The arrangement of these items may be vary, but the concept is going to be the same. So here you have an same images. So from this you can find out the defects, the cross layer. So this is magnified with a nano level scope. Then Here you have an layers. The layer formed is not an same, that is not uniform as crossing. Then the distance between the vertical distance as well as the horizontal distance is going to be varying. So that type of formations, even the layer formation in the previous case, what the things shown is you have a layer formation using a powder fusion bed. So the middle, the powder particles are not centered, as uncentered particles. Then the layer having a break. So you have a layer, short layer. Then one time you have a long layer. Then sometimes it may melt within a cross. So you can get a cross layer. Here also you have a small layers. The layers will be in the cross one. So the first defines, you may get the cross layer. One layer will cross with other. Then the layer defines, not in a uniform one. You have a short, lengthy, etc. So in the cases, in the micro level or in a nano level, if you are testing that part, it may withstand on a high load. Suppose all the things are uniform. Otherwise, it will be giving a less load. The load bearing capacity will be decreased. Either the part may be subjected to compression or a tension, or you have a shear or some twist. Whatever it may be, it have going to give a different reaction depending upon the internal structures. So what are the tests you are going to do? That is either the shear test or a compression test or a tensile test or a torsion test. So that variation will be correlated with the internal material composition and the layer formation or the particle melting conditions. So either it's uniformly melted or not melted, or sometimes the particles may be, the powder particles may not be consolidated. Here you have enough particles are separated. So you may have a small. So that size is in a micro, even some nano. In that cases, that will be entrapped within the particular layer with layers. The surrounding will be melted and consolidated, but some particles may be unconsolidated. So in the cases, you have a different behavior in the testing, or wherever you are going to use that particular part. So the next one is porosity or Y. So here you have is clearly shown that there's a void and a gap, or some the bubble formation from the porosity. So these things you can get from some images. So these things are coming from that one, that is how to follow the AICTE standard. Even the AICTE standard, it may happen in the less percentage. The less percentage in the sense 0.5, less than 0.5 is acceptable. So even the density calculations, the density of that packed material. So you have a definite formula. In the formula, that value is less than particular value, you can get a dense packing of the material. So otherwise, it will be having enough void and porosity. It will be having enough bulky. Even the record size, we may have a more number of pores and voids. So in that cases, its strength may be going to be reduced. So depending upon the application, suppose if in a high risk area, the material, so that will be leading to this. So here you have a layer formation. This layer formation also you have a in between, you have a dots, then voids, etc. Here the hard isostatic pressing. In that one you have a small this layers are even in a small dots, it will be occurred. We can get from that image, there's a 270 micron micron images. So the next one is the draft border. Some of the border will be drafted within that one. Either the chance at having it have no chance to melt. So the layer after that layer, if you are having a layer formations, this is magnified one. The layer, this thing is a magnified one. So here you have some enwrapped powder particles are in a raw material. So it may melted or sometimes it may be just impinged on that layer. Here you are giving in a heat energy and melt this one. So the heat energy may not occupied by the particular powder in the sense the powder will be entrapped within that pot. So due to this, nothing will happen. If you are visually seeing that one, the pot will be very nice, very good aesthetic look, the finished condition, even the surface finish will be have a very smooth. You can use and roughen our body, there is no problem. But where you are going to apply? So you are going to apply in an engineering application in the sense, in that engineering application, the particular one may require to withstand a high tension or a high tensile force or a high compressive force or a high shear or a torsion load, something. So for that, either it's withstanding or not. So you have to go for that. Even this technology will be giving in a more strength compared than the others. That is normal conventional method. Even you have a 10 mm shaft in a MS steel, the normal method you are manufacturing, that strength is somewhat lower than that same 10 mm mild steel manufactured in the additive manufacturing. Here the grain structure, everything will be very fine compared than the normal conventional method. But even though that strength, everything will be increasing. The defects will lead to the failure at point. And finding also very difficult. In the normal conventional material, you can easily cut and get the defects. Sometimes in the spare eye, you can get a defects. While cutting the mild steel, you can get some of the force or flaws within the side. But if you are manufacturing the same part in an additive manufacturing part, it's very difficult to find out. So here you have different types of defects occurred in the powder bed fusion technologies. That is the powder based fusion technologies used in a laser sintering and selective laser sintering, then direct metal laser sintering and electron beam melting is even the selective laser melting. Here, the direct energy deposition method. In that method, what are the defects? The direct energy deposition, what you are going to do? So you have a heating source, either the laser may be collimated and focused in a particular substrate. In between that, you are supplying the feedstock, either powder or a wire or whatever the thing. The control of the feedstock will be done. The depositor head will be there. So you have a feedstock in this side. You have an energy, that is heat energy supply from the top. So the controlling of this feedstock or a powder supply, you may have an inert gas, etc. The bottom substrate, you have an additive manufacturing. That is, this will be melted and deposited over. You are directly depositing on the substrate by a layer by layer. So in that cases, what are the defects it may come? So you have this is an images taken from that same scanning electron microscope. As soon as that defects are represented for a direct energy deposition group of additive manufacturing equipments. So here you have an over surface finish. So what happens? You are depositing material on the substrate by layer. Will be deposited in the layer. So it's may have an poor surface finish. Even the poor surface finish will be very good If you are seeing or touching that one, it will be very fine. But if you are going for an nano level analysis, so you can get a surface freeze will be low. So this how it's happening. So the end or the part you have on a rabbit speed or the deposition, the feed and feed rate, everything will be coincides. Then you have a correct deposition. For that you have a standards. So what standard you have to use? Then you have a formula, that is the energy rate. Specific energy is what? The specific energy is varying. It's varying. You can have a defects in the direct deposition. So you may have a porosity. So the same cases in the entrapped or some of the gas, even the small gas, even you are using an inert gases for that purpose, that may be entrapped in the sense you can get a porosity as well as void and holes also it will be created. Then the incomplete fusion. So you are depositing layer by layer. So similarly in the fusion powder, fusion bed. So in that also the incomplete fusion, that is this not melted and consolidated. The powder is not at all melted, then only it's trapped within that one. So same cases having the direct energy depositors. So here you have an incomplete fusion. Then in the particular things, you may have an undercut, that is you are depositing one layer to another layer. Above the substrate, you are forming a number of layers by layer by layer. That is printing in the line by line, covering the surface, then line by line covering the surface. So in that cases, you may have an undercut. The undercut also will come. So once the fluctuation of the energy supply as well as the other feed rate, you can get the things. Then the cracking. So this will be propagate once there is a void or an other porosities. It's a chance to having a crack. So what are the standards I have to follow for this one? So if you are comparing the density, considering the density alone, for a density, so I have to follow the ASTM B212 density. That is for a free flow powders using a. So you have to control this flow conditions. Then similarly, the other things are used for a different density and the other selected part. Suppose if you are using a helium and hydrogen for a particular gases used in the direct energy deposition, so you have to go for this thing here, the helical density. You have to consider this one. So the density, once you are used to the Arnold meter, you can go for this one. Similarly, in the flow rate, how to control this one? You have to follow either any one of the ASTM to control the flow rate. The particle size. So the particle size, you have to use the ASTM standard base. Then the CO analysis, particularly CO analysis, used for finding the particle size. So as per the ASTM standard, you have to follow any other one. Then the sampling also, if you are testing the powder sample, you have to go for a sampling as per this ASTM. So here, that's a standard used for even the process parameter. Then the things are mostly happen in the mold pool. So from that, you have to get an ideas. So the ideas now you can derive using a high-speed infrared thermography. So this is normally used to obtain the imaging data for the prediction of microstructure. So the microstructure will be taken from the particular part using a high-speed infrared camera. So the same thing will used to determine the grain size. Once the microstructure images are taken, the images will be interpreted interpreted in a standard method and finding the grain size. So here the melt hole you have to consider. So where the most of the defects are coming from, that one is a melt hole or the melting area. So the first one you have to go for that one inspection of this one. The purpose of the process control over everything. That is, here while doing the process you can control the parameters. So the parameters will be based on this thing. That is, you have to go for a different flow rate or a different particle size for a different density, how you have to do. Then here the process control also you can do on the online. So ongoing process, I have to see that one and check the one. So here the process control to put to effectively use such information of the images from additive manufacturing process have to be processed at a speed of at least 30 kilohertz. So the 30 kilohertz, in the sense, you just imagine 30,000 frames or 30,000 images per seconds you have to analyze. That is what happened in the particular system. So you have to online in the process control. Here, what are the informations you can gain? So in the inspection, controlling of this one, so you have to go for a material composition and phase transformation. So how the material composition is there, then the phase transformation. Even the SEM image or in TEM images or in a thermography, you can identify the different composition, because you know that each material having a one natural radiation wavelength. So in a particular color, it will radiate the particular radiation. So it's natural is that if you are capturing that one, all the materials, suppose nickel, chromium, steel, this iron, iron, aluminum available in a pot. If you are taking a photo, it will giving in a different structure. Even the photography is another pixel oriented, color based. So they initially you have a black and white 0 to 16 colors. 0 to 16 colors. 16 colors in the sense even the black and white will be varied by 16 shades. Now you have a number of colors, the 5, 12, 1024 colors. Even if you want to do that one, you can increase that colors by varying shade. Like even the blue color, you have a number of shades. So that thing will be used for a composition, material composition analysis, as well as a phase transformation. That is, either it's transformed or not. You are putting in a powder, the fusion bed, the powder fusion bed, powder is there, either is transforming or not. So you can easily find out. Then you can control. So once it's not transformed, phase change is not occurred, you have to go for the specific energy. Whatever the energy striking on the particular powder is not enough to melt. So otherwise, some particles are melted, then the other thing are not melted in the sense. So the focus is somewhat varied. So it's focusing on a corner or on a right corner, left corner. Some particles are not able to melt itself using that specific energy supplied by the laser or any of the heating source. Then repair of existing defects such as presence of pinholes, porosity, microscope cracks and segregation. So the online things will give an idea of repairing the cracks or pinholes or porosity or whatever the things. You can watch that one. So suppose the material is not melted, you can increase that specific energy striking on that particular area, or I have to move the head. So which one I have to do? You have to identify that one and do the things. Then particularly the manufacturing here, so you have requirements. They introduce measurements of temperature, cooling rate and residual stress. You can measure the temperature you have a number of pyrometer, high temperature measuring devices. You can get the temperature of the particular process. So you can onlinely do that one. Then the cooling rate, how fast it's cooling. Even from the temperature measurements, you can also identify the cooling is happened or not. Then the residual stress, even the magnetic inspection can identify the residual stress also. Or you have a radio test, that is radiosity test, you can identify the residual stress. Then the calibration of all optical sensor used for the purpose of high accuracy measurements. So in the defect, whatever the things you are coming, you have to consider all the things to nullify that one. Then in-process monitoring of not only the geometric dimension but also the surface quality of the finished layer. So even the continuous monitoring will give these things, that is either it's present or some cracks are present or not. Then that will be rectified. In similar cases, you have to check the geometric dimensions as well as the surface quality. And here the selective laser melting, so it's a simple thing. Here you have a diagrams, the manufacturing methods, it may be explained in the previous classes. Here, how the process monitoring you can do. So that is even here. So here you have to use a scanner. That is, apart from the equipment necessary, complementary system can be incorporated in the machine to enhance the process quality. So here, what happened? We are giving an additional things. The scanner, the images will be taken from continuously. Then the camera that is focused on the particular part. So this thing will be giving an additional things. So what happened in the selective laser melting? Here the part is manufactured. So this will be continuously monitored by an infrared camera as well as the other scanning devices. It will be continuously scanned. Then you can get either this melting or not. Even the layer by layer, if you are getting another 30,000 frames per second, in the sense not an easy. Then the analysis also you have to do, take more effort to analyze that one. So in that cases, I have to minutely watch. For that also you have an analysis software, the images for this much frames. Even in a high-speed camera, the high-speed camera sometimes you can take even in a 50,000 frames per second. In a high flow analysis, they are going for even lakhs of frames. The cost of the equipment may be goes on increasing. So here, if you are using that one, then the unique monitoring system installed on the SLM machine developed in-house. Here, this one industry, that is in a research industry, they are using the own things to monitor the SLM process. So the images will be continuously taken and identified what happened to each process, each seconds. Here the typical melt full image during the process. So this is a melt pool, because there only you have wherever there's laser striking, there you have a melt pool. So after that you have solidification, that is the bottom will be solidify. Here also solidify. So the current thing is here. So what happened? You have a center. Only in the center you have a melt pool. Around that one you have a solidified one, or here you have an unmelted things. So from that center, the heat will be propagating. Definitely these things will be melted. Suppose this not enough to melt, what happen? You have a edge effect or end effect. So the surface will be in the normal feedstock material or in a half melted. So in that cases, the strength as well as any of the testing will done, the material will behave in a different manner. Here the material will be behaving in a different manner. Here it may be behave in a different manner. Then other side also you have. So for that, I have to consider that flow rate also, the material flow rate also. How much time you have to melt? Then only it will be completely melted and salted. So that will be happen. Thus arrangements of this one is schematically shown here. Here the light shaded arrow mark represents the laser radiation that's melting things. Then the black shaded one is not melt pool radiation. So from that one, you have an images. It's interpreted with either this entire pool will be melted and uniformly and solidified or not. So here you have an working plane. From the working plane you have a scanner for focusing length. Then you have a semi-reflective diachronic mirror laser source output that will be comes and focused and striking on the melt pool. So in between you have an optical filter, the beam splitter, then detector. You have a detector in the upper side, then the detector to the photo diode with focusing optics, then capture image captures also. So here you can continuously monitor that one. You have to inspect what happened to the process. The melt pool also what happened. You have a melting of this thing either uniform or not. Then it's propagating or for a fraction of a second it's allowed to melt or not. So you have an and the quality issue arised here is what. So it's not basic method and you're monitoring or inspecting continuously using the system of setup, then the quality things arise. So what are the quality problems arise? So the Q represents what you have on a heat transfer in this particular part or in this direction, in this direction. So here you have a substrate. If you're going for this one, the bottom have a table, in the bottom only have a substrate. So here the laser film is focused on the powder part or some other feedstock. Here the layer will be formed again, the layer will be formed again, it will be formed like this. Then how the surface of that is the powder is here, you have a melt pool. The melt pool comes and goes up. Surface evaporation is possible. Surface evaporation is possible. So here you have a surface evaporation in the sense the other side you have a consolidated material. So if I have any diffraction, that is the cooling rate variations, or if not cooled properly, it will be locked within the things. Then you have a formation of the consolidated layer, this material. Then the melt pool, these things. Here, what happened? You have a rapid solidification effect. Some places may rapidly solidify, and other quality issues are arise. So different zones, you have different zones, the flow of the melt and evaporation will be vary. So here the entire thing will be melted, so consolidated. Here you have a slow consolidation. So what happens if you are having a testing of this material? So along this direction also the property will be vary. That is the things initially they are till the research or analysis is going anisotropic. Is now the potential things available in the particular one is a porosity. The porosity is a common defect. So either selective laser melting. Because the powder consolidation process is driven only by temperature changes, gravity, and capillary forces without the application of external force. So once the gravity based in the sense that most of the time you may have to get on a porosity. The cases that is the top, you have on any pressing. Even you know that the casting and forging parts having a difference. The casting you may have a porosity or an internal, but in the forging you are compressing out, giving in a compressive force, skews and recrystalline the material structure. The current structure will be reformed, recrystalline will be happen. So in that cases, it will occupy the gapless or a poreless grind structure. So that is a normal things happen in the casting and forging. So here, because of this natural feeding and changes, the gravity based, so it's a possibility of porosity. The porosity can be formed as large irregular pores due to lack of melting, shrinkage, micropores due to lack of feeding. So the small micropores will be shrink once the feed rate will be differ or varying. So within the intertemperature zones, and 25 the spherical micropore, the pores also happen in the drop gases. So even in the things are used as a inert gases or some of the supporting gases in the sense that gases may be entrapped within the part. In that cases, it may form a porosity. Adjustment of the laser processing parameters can improve the densification of the above up to 99% of the theoretical full density. So here the porosity is increased in the sense you have a density variation. So once the density is increased, that is for the same volume, for the same mass, you have a volume. So that volume will be dense, compressed, or exposed packed, or upon the voids and the pores will be decreased. So here for that one you have to go for a less of the processing parameter change. So here the results of the particular one that's taken from a SEM images. So the scan speed is shown here. There's a space, scan space. Here the pores are given in a different colors. The dark spot. So once you have an images, the major part is what, minor part is what. So the energy used for each one is represented. The particular images is this, that is 139 joule per mm cube energy is used. That is, this energy is in a specific energy or the energy per volume that is used. Here you have a 96.92% of dense. So it's decreased, the energy level is decreased. You have a density variation, it's decreased. Again, if you are increasing the energy level, the density is increasing. So you just see that one, the pores or what happened. So you have less pores, you have an increased. Then again you have in between them. This one is going to be implemented in the force reduction. That is, you have a force variation. So here, in the presence of built parts, the particular performance of some built parts is particularly determinable to mechanical strength and fatigue performance. So whatever the things you are used here, that should be applied for any of the engineering application or in a commercial application. So that must tested for either the mechanical strength or fatigue performance. So here non-spherical porosity is attributed to either instability in the melt pool or insufficient energy density. So the insufficient energy density results in lack of fusion, then you can have a defects. So that's why this the energy level also shown for each diagrams. Whatever the piece taken, the piece manufactured using this particular specific energy, the energy density. So the phenomena of quiescence of particle to melt pool can also be used to understand the influence of hatch spacing, then center to center distance between the melt pools in the build plane. So what are the hatch spacing? We got a diagram. So this is a hatch spacing. So here you have one particle, so another particles is overlapping. So from that apex to apex, what is a hatch spacing? So you have a substrate or in a previous layer. After that you have a next layer. If you are going for a formation of next layer, then the hatch spacing will be given. That is as a particular parameters. The phenomenon of quiescence of particle to melt pool can also be used to understand the influence of hatch spacing. The hatch spacing, what happens? The one particle will overlap with other. Suppose if you are going for a micro and a nano level analysis, the particle size may be 10 nanometer. The 10 nanometer particle and 10 nanometer particle will be overlapping in the sense. So in the bottom you have a small gap. So you have packing the particles. So in the nano level, so you have to put on a small 20 nanometer, 10 nanometer small circle. In that circle, what happens? One will be overlapping other. If you are arranging the same thing in line by line, layer by layer, what happens? Even in a 4 particle, you have a middle, you have a gap. The gap must be filled while melting or getting a specific energy, the energy from a laser or any of the melting source. So suppose it's not happening, it will be occupying the same place, that's the end drop particles. Then the one will be overlapping with another in the sense, what happened? So you have an ununiform gap between the 4 particles and the next 4 particles, next 4 particles. In that cases also you have a difference between one segment part to another segment part. So here these things are influence the hatch spacing, center to center distance between melt pool in the build plane. As the hatch spacing is increased, the line of porosity and unmelted powder form. The hatch spacing is increased. It will be leading to this porosity and unmelted powder form. The flipped around the hatch spacing at which parallel tracks coils become the indicator of the limit of the resolution. Limit of the resolution of the particular system you are making, even the cellular structure or whatever it may be. So there's an porosity based things. Here you have a hatch spacing in a particular images. The images are given in a different nanometer, this micrometer images. For each images, if you're going for this, you have a 200 micrometer images, then 300 micrometer, then 400 goes on. If you can see it goes on, you have another particle size. Particle size will be there. Then either it's uniform or not. So this will be increasing in the sense that time it will have a force. The line, the spacing is increased, porous, there is line of porosity or unmelted powder form will be there. So it will be giving an unmelted part. Even here the side you can see that particular part, even the powder particles. Here the size, everything is given. It's a titanium 6 aluminum 4 180. Okay. So the hatch spacing is this thing that is here is just represented for an understanding where the hatch spacing come. So each particles. So how to avoid this porosity? Where the operating conditions for a different material. So here is the effect of porosity is based on this one, the specific energy. The specific energy is correlated with the enthalpy of melting point, that is enthalpy of melting point into this group. That's surface absorbability, then power, whatever the power supply, the density at melting, density at melting. Then you have a values like this. So here the HS will be cancelled. So you have the specific energy terms alone. For a different material, there's an ASTM standard. For a different material, what is the enthalpy at melt required? So here titanium 6 aluminum for 1 medium. Then stainless steel, you have aluminum silica internal, then 316L material. So you have different things. For that, you have a parameter to control or follow. The standard will be followed. Suppose if it is varying, we can get the porosity problem or some other voids. So here the TELH based, you have a discussion. The TELH is for one TELH for a particular specific energy, the density will be less than, that is the porosity will be less than 0.05 or very, very less. So these things are discussed. Here you have the energy parameter, here the volume based density, energy density are considered. So here it goes on increasing. The value are increasing, the energy level is increasing, you can get a less void or porosity. So here, this parameter, at one specific energy, here energy density is given. For a specific energy, you have a less porosity or 99.99% of high density, a highly compacted. So for the cases, I have to consider the various variable. Even the speed, half width of the beam spot, the width of the beam spot also have a variable. So these things are fixed for a particular material. So if you are going for an analysis of using an optimization techniques, suppose if you are taking a tungsten, titanium, aluminum, vanadium things, you have a requirement is specific energy in the sense you can go for a power, half beam spot, speed as a variable for the particular problem. So for that variable combination, when the density, the output will be in a density parameter. The density is high, you can easily find. So here the discussion is given. Upon inspection of this normalized result, it appears that there is an optional range of TELH by HS. The enthalpy of melting at melting point, thus TELH is a specific energy wherein fully dense. It is now fully dense for a particular range, it will be fully dense. So how to, we can find out that particular range where it is fully dense. The samples can be obtained regardless of the material type and the process setting. So here, different types of material. For that one, the values are given. So that's regardless of material type and process setting, you have a particular range to give a fully dense material. That is, the porosity is less than 0.5 percentage. So that is an acceptance case, acceptable level. The acceptance of porosity level would be based on new standards, reference images similar to those that are already available casting. So these images, what are the images we are taking from this SEM thermography? This will be compared with the already existing ASM standards of that. For that, you have to compare with that one. So here, for an titanium casting, the ASTM standards are given. So that is E2669. So I have to get the images of the manufactured one, AM manufactured one. Then you have to compare with this standard. Either it's fully dense or not. Or how much percentage it's dense. Or how much percentage it's having in a void or a porosity. And similarly, for an aluminum casting, you have an ASTM standard E2422. So this image is a reference. And what are the images we are taking from the current, or what are the work you are going to do in the aluminum things, that will be compared with this one. So the next major defects is balling. The balling occurs when the molten material fails to wet the underlying substrate. So like in what else? Tamarai. So lotus leaves. If you put it in the water, it won't wet. It will be just roll out. So here, as roll out, the roll out, while the water shape is like in a spear or in a somewhat rolling element. The 99% is in a sphere. That's ball. That's rolling. Same thing will happen here in the things. The balling occurs when the molten material fails to wet the underlying substrate. Sometimes the top powder will be melted, the bottom is not melted, the energy supply, or the head is moved. That is moved in the sense the top is melted, bottom will be unmelted. So that will not wet with the or combined with the bottom layer. So you have a small gap. That is, that behavior will be n-drop particles. Then the strength as well as other parameters, rather than the fatigue, even the fatigue things, the crack will be maybe initiated from the low strength particles. So this will be leading in a balling of the things. Here, the underlying substrate is not wetting due to the surface tension. So the same like lotus leaves and water interactions, then spherizing the liquid. So the liquid will be like a spherized one. So the ballings are like this. You have a limited liquid formation. So it form a balls. So here sufficient liquid formation, so it's continuously central drop. Even the unmelted core are here. So this is a powder bed. The powder bed layers of beams are striking here. By striking that one, you can have a formation of either no centering neck formation. So the neck is not formed. In that cases, you have a unmelted cores within that side. The liquid is not enough to melt the remaining balls. Then it will be forming in a circle alone. So the liquid is more, it will be forming a neck formation, centering neck formed. Then try to melt. So here what happened, this because of the surface tension, it will be keeps on the same place, same things. So even it may recapture the heat from this thing, the liquid, it may melt, but the without neck forming, then again it will be lineated, then it will be having a layer. It will be forming a normal structure. But it's once formed, it may form a gap between that one, or it's having a cooling and saltified, that is saltified in the separate one. It won't touch or mix with the interpretation with the one layer is not possible. So this balling result in a rough and bed safe scan tracking, increasing the surface roughness and increasing the porosity. So even the ball forming is in a circle, so that may not forming a neck then layer. That is not possible. It's forming in a circle. The circle, then neck forming, then it will be goes for a lineating, then you have a layer. The layer not formed. So that case is what happened. If it is circle in the sense, the top you have enough 4, the bottom you have enough 4. So there is a possibility of increasing the porosity. Similarly, the roughness. If you are having a micro level things, it's not lineating. So you have a roughness. So here you have a peak. Another value will be in the down. So in the cases, so the peak is here, the value is here. So the roughness will be increased. So it is melted and lineated. You can have a straight line. So generally, both material property and processing variables can influence the wettability and consequently piling. So you have to go for the process parameters, how to control this one. So for a particular process parameter, it may be in a perfect things. It won't create an unwettabilities. That is, it won't create any balling. So for that, you have to find out the process parameter, the optimization process parameter. Because of liquid metals do not wet surface oxide films in the absence of chemical reactions. So suppose the oxide films, everything is some other layers are formed that also not interpreted with the next melting pot. Even the welding, you can get a layer on the top, axial layers, even though you are using a flux in the welding rod. Finally, you are chipping and removing that one. Suppose any of the axial layers form, that also giving problems. So here it is very important to avoid oxidation and contaminations. So I have to avoid that oxidation and contamination. Another possibility to improve wetting is the addition of certain alloying elements such as phosphor in selective laser sintering of iron-based powder. So you can have an additives like that. You can increase the wettability. That is, you can do. So here normally encountered in SLS and SLM. So this is a fractionation of the melt pool or ejection from the melt pool. So from the melt pool, it will be comes out as a separate. That is separate in the sense it will be forming in a own shape with that one. That is, it's ready to form a different shape. It's not ready to attach with the other coils with the other things. The fractionation occurs when through surface tension effect achloramates form. The root cause for the phenomenon is the incomplete melting and fusion of the particles that occurs when process parameters are incorrect. That is, the energy density is low. So whatever the energy density you are having discussed, here you have to go for an energy density. The energy density is joule per volume. So the previous case we are shown here the energy density. So that's parameters you have to consider. So this is now a symbolic representation, the schematic representation of the balling things. Here you have same images. I have to inspect that one for a particular product. So even in a laser density, that is the power given and the scan speed. So you can get on a different formation of this balling, the droplets. Here you can see that one does not separate form. So you're getting the nano level images. That images also you can form, that will be shown in a ball-like structure or a gloomy of or an agglomeration of small particles. So that is you can get from the same images. So the residual stresses, here the residual stresses we can easily find it from a normal method. Here the residual stresses originates in the solid layers and the substrate underneath the newly applied layer. This imposes tensile stress on the newly deposited layer. So the one layer and another layer, the cooling and shrinking, that is the cooling rate is varying. You can get a shrinking, the one layer will be shrink high or one layer will be tensile, that is expand more. In that cases also you can have a strain, the strain, induced strain, that is a residual strain will form, then the stress will be automatically inbuilt. Here is the tensile stress will be deposited on the new layer and creates a compressive stress at the bottom layer. Residual stress will be partially relieved after cutting the part from the base plate, causing some deformation. So normally the stress concentration or the internal stress will be relieved by giving a notch or a hole or cutting some portion to relieve. So here the stress is usually tensile at the top and compressive at the bottom. Depending on the commonly unfavorable effects of the residual stress, a subdivision of scanned area or smaller scanning section. So you have to go for a scanning of the particular section. Then the heating of substrate, then post processing can be employed to mitigate the residual stress. So here you have to go for a scanning and other things. Heating the substrate is either uniform or not, then have a forced process to relieve it. The cracks is another major problems. The cracks commonly originate from the high temperature gradient between the melt pool and the surrounding solids, leads to excessive thermal stress and rupture. So the previous one also in a strain because of the uneven cooling, one having a tensile, another one having a compressive stress, then you have a problem. So this thing will be scanned. That is the scanner you have to, then the scanning or the depositing you have to regulate, and then you have to maintain the temperature. Then here you have a cracks, that is because of the high temperature difference in the gradient between the melt pool and the surrounding. So it may lead to cracks and initiate that is due to this thermal stress and ruptures. The compositional segregation in some alloys may intensify the cracking. So here, based on the material used, suppose if it's a ductile material or some other things, it may lead to different behavior compared than the brittle material. The alloys that are prone to hard cracking and solidification cracking have been proven difficult to process. So already we have some of the materials having a proven crack for the cracking in the hard conditions. So these things are maybe avoided in a particular processing SLM. So here the scanning strategies are given. The different scanning strategies affect the thermal history during the SLM process and considerably alter the material properties, including density, thermal and residual stresses. So here even the same thing will be captured continuously. You can capture the image using an infrared camera at a high speed. So the thermal stress, residual stress, and the microstructure you can refine using different types of the scanning strategies. Here the scanning or in a deposition of the material will be in a different values. So here the fill contour offset, that is the inner side is a fill. So here the number of layers, each layers will be in a different directions. Here the particular one representing the parameters that can be altered to improve the quality. So you can continuously take an infrared pictures while doing this one. What happened to the surface material? Then the thermal or residual stresses deposition. Even the thermal images, whatever the things you are taking while processing the material, it will give a hot spot. The different temperature, even the colors are nothing but radiations. You know that. The same thing will be we can get from the thermal images where the high thermal intensity is there, where the light thermal intensity or the temperature is low. So we can easily identify that one, which one is having a thermal stress, or from where to where the crack may initiate because of this thermal difference or temperature difference. Here there's boundary parameters, then a scan line offset, then fill contours, increase precision and quality of the border. So what are the way you can scan? Here the scanning, one is unidirectional, there's a bidirectional. So you have to scan like this, or this even the printing is in a particular direction or in the bidirectional, or you can go for a 90-degree or in a different angles. Then even the different methods, the chessboard method. So in each cases, I have to capture the stress distribution or the temperature variations within that one. Even because of the hot pole or a melt pole, the cracking and other parameters are initiating. In the sense, you have to monitor all the things using a pyrometer. Even the temperature the pyrometer will give a particular point temperature. Suppose if you are going for a high temperature imager, the high temperature imager will give the entire things temperature image. So you can identify what the temperature at the pole is high and low, how the stress will be formulated. So you can get the ideas of this. Then the electron beam melting, the process parameters may have a significant effect on the part quality indicated in the variations. The melt can, that is the previous one, scan the beam current and the scan speed affect the EBM build effects such as porosity, which may be related to the microstructure or a property variation in the final product. Even the delamination is also possible. There is the ultrasonic consolidation. Ultrasonic consolidation is another method that's in the additive manufacturing. So in that one, the layer by layer, they're using the same ultrasonic sources. We can do the layer by layer joining. So in that one, the delamination, in the sense the layer will be detached from the previous layer or the top layer, succeeding layer. The layer will be detached, in the sense you can get the delamination. The delamination also you can easily identify using the scanner. Here the computer tomography analysis we can go. So in that one, some of the particle size you can measure, even some porosities, the other parameters also you can use. Here the particular one used is represented microphotonics SkyScan 1172. Here the image pixel, the equipment image pixel is 2 micron. The voltage used to is 100 kilovolt. The image analysis using microcity data was conducted to determine the porosity of the sintered powder. The particle size as well as porosity you can find. So they are measured by image J software. So again, the digital image processing. Whatever the things you are taking, that images will be processed in the digital manner. For that, each equipment suppliers having a different digital image software. So here the particular things you have an image software. Moreover, the particle size distribution were quantified from image analysis using an image flow sum. So once if you're buying this one, the accompanied software will given. So what are the things the captures you are taking? From that one, you can easily find out the porosity as well as the particle size. Then the specimen enclosed. Have each cases, suppose if you are going for an SEM or a TEM or any type of testing, each testing you have a specimen size. As per the standard, you have to use the specimen for that one. So here there is now 4.8 mm length and with this both the things are 4.8 length and width and 6.5 6.6 mm in height. That closed part chamber that will be used for an analysis. Here the ASTM round robin test to illustrate the result. So here you can find out the changes in the interior part. So how the images will be improved. You can see that here no screening liquid is used, standard resolution of CT. Computer tomography is used. Okay, computer tomography is used. So you can identify the porosity as particle size. So the images are improved by high resolution CT. Here the standard computer tomography. So you are not getting the insight of this one. So if you are going for a high standard, then you can get some of the insight, the small changes. That is clearly all the parts will be same. The differentiation is the inner small things. Similarly, if you are using a screening liquid, even the magnetic resonance scan, MRI scan, whatever the scan you go, somebody is putting some liquid, the screening liquid. That liquid is improving the image capture and the visibility of the images. So in that cases, here the N for fluorodecaline screening liquid is used for the CT. Now the images are improved and you can get an internal details. Then you can easily identify the 4 RNA particle size. So this will be magnified. You know that for a square inch or a square mm, what's the image you are captured? That image will be magnified. In that image is how many particles or how many pixels are there. Based on that one, you can easily find the particle size. Even the porosity also you can find it. So here there's a part manufactured using a titanium, aluminum, vanadium based material. So here the another test to find out the end effect, undulations, the coarse phases, radiometric analysis. In the different parts, the images are taken from the radiometric. So here you can easily identify that is the end effect. The ends are not straight, or you have a small changes in this one. So in the previous case, even the deposition energy rate, everything is variable. If you are depositing line by line or in a unidirectional or bidirectional or something. So the specific energy is varying in the sense. What happened? So one time, one edges may have a deposition less or a high. That is, melting will be not there. Suppose not melted. In a particle, one particle is not melted completely. The time the particle will be gone out from the pot. If you are bringing into vertical directions, it will be down. There is not wetted with the other particles or other layer. It will be goes on. In the cases, you can get an end effect. Using the radiometric analysis, you can have a end effect finding the undulation, the things, then the course, finish, etc. So then the thermal images, you can go for a full analysis, full temperature analysis on full what happened, milk pool, what is the things happening you can do. For that you have different types of equipment, the Micron M9 2000 high temperature imager or Micron's M7500 low temperature imager. Here both of these are measuring the different things. There's a multiple temperature, there's a bulk temperature part. So the far associate spectropyrometer also used. Here high temperature pyrometer is used. So you can get an thermal images also. Here there's a multiple thermal analysis, that is in the pictures. So the temperature is given in this part. The temperature is given in the pot. Okay, I hope that's going on. So you can change that one, that is the different conditions it's taken. So how it's varying, that's shown here. And similarly, the thermal images, that is this taken as a Phoenix PM equipment, particle ejection from a melt to pool during the selective layers of melting. That is this thing, the particles emitting, how it's ejected, so it's uniform or not. This is using an IR camera. Also the acceleration time is 50 microsecond. 50 microseconds in the sense you can consider that how many frames you can take per second. So this is another images from an IR snapshot using an electron beam melting things. Here the fallout time is 3, fallout time is 15. How the particles are varied, layer 1, layer 2, layer 3 and layer 4. How the formations are there, that the particles image is what, which one is consolidated and unconsolidated, the solidified and unsoldified things. It is a scintillating process to find out the voids or inner details. So there's a radioactivity things, it will giving an emission. That emission will be counted either in terms of counts per minute or in a disintegration per minute using some of the isotope material. From that you can find out either the inner side, any of the defects are there. So this is one thing used by the US Air Force for different things, that is different types of testing that is used for particular applications. So you have a visual testing, leak testing. So where you have to apply this one, Maryland fraud types detected is this. It defecting there is no global screening or detect location is barrier, the surface or location. It detects or locate. You can get the surface or interior, either on the surface or on the inner side. So you have all the type of normal things: visual testing, leak testing, liquid penetrant testing, process compensated resonance testing, impedance computed tomography or an electrical impedance tomography, then alternate current potential draft, eddy current testing, then array eddy current testing, phase array ultrasonic testing. So the ultrasonic testing is detects and locate the defects. It's giving in a surface defects and location as well as the subsurface. So this is the list of tables used for that one. This type of things also you can use for an inspection and the testing. So I hope within that one I conclude my presentation. Any queries? I hope I go beyond that stipulated time. Sir?